Determine whether the following series converges or diverges. The sum from 1 to infinity, 1 over 2 root n minus the cube root of n. The terms of this series definitely go to 0. The denominator grows while the numerator stays constant. And so we can't use the test for divergence. This would look a lot like a p-series if one of these terms were missing from the denominator. When you get something that looks a lot like a p-series, then you should do the comparison test. There's two of them. There's the direct comparison test and the limit comparison test. If it's not too much trouble, try it. Try the direct comparison test. It relies heavily on an inequality being true, but if that's true, you're done. The limit comparison test relies on your ability to be able to calculate a limit. In both, though, you have to go out and find what dominates in both the numerator and denominator. Well, there's only the 1 in the numerator. In the denominator, we have a root, square root that is, and then a cube root. So who's going to dominate as n gets large? If you take 100 and take its square root, you get 10. But if you take its cube root, you get something much smaller than 10. There's a number out there that you multiply by itself, multiply 3 copies of, to get 100. And that definitely would be less than 10. And so, because of that, then we must say it's somewhere between 4 and 5, I guess, because 4 cubed is 64, and 5 cubed is 125. So anyway, we should use the root n as a dominating term in the denominator. So for the comparison, we would make our bn be equal to 1 over 2 root n. Whether you include the constant or not is up to you. I like to include it. It makes saying my inequality is true easier. And so, but never go get a bn where you don't know what the series on bn does. So the series on this would be, since you brought that constant in, you can pull it out. It'd be you're looking at 1 over n to the 1/2, and that n to the 1/2 is a p series, and when p is less than 1, then it's going to diverge. So you went out and got a series that diverged, but pretty much your series is going to behave like this as long as you can show a certain inequality is true. When you go out and get a divergent p series, or when you go out and get a divergent series with the b sub n, doesn't have to be a p series, what you need to be true is that your b sub n series needs to be always larger than the a sub n series. The a sub n series is always, it's what we generically call the term that the series that you're given. And if that's true, then by the direct comparison tests, they'll behave alike. Here's the reason why. If your smaller guy, b sub n, diverges and a sub n term by term is bigger than that, then as you add up all those terms, it has no choice but to also diverge. It's smaller than something that's going to, it's bigger than something that's going to infinity. It must go to infinity too. And so we just have to convince ourselves that inequality is true. Bn is less than an. What's the difference between these two? The difference is the presence of this cube root of n term in a sub n that's not in b sub n. So what that does is that makes a sub n have a smaller denominator. And if you have a smaller denominator, all other things being equal, then you're going to have a larger fraction. So that's one of the main reasons why I put that 2 in there, so I can make this comparison more directly with less effort. Alright, so you went out and got a divergent p series, and your b sub n sequence of terms is less than your a sub n sequence terms. So when you go to add them up for the series, they will do the same. Since your bn series diverged, then your an series also diverges.